So the first thing that I want to discuss is the discussion board for this week. It's going to give us a good warm-up it's going to give us a good opportunity to define a bunch of words that are important that I'll be using left and right for the whole semester. And you may think, once I define them, you may think, well, gee whiz, those are trivial, silly. Why are we talking about this? Waste of time. But I assure you, it's extremely important. And very interesting as well. So, let's give some definitions. An identity. In algebra, an identity is a number such that if I use an algebraic operation and take this identity and, like let's say I'm adding for my operation. Well, I want to take this identity and add it to whatever number, and it comes out identical. It should come out identical. So we can say identities behave like there's some number, there's some operation, like maybe that's plus or times, some operation, and then here's my identity. It comes out the very same. It started off as A, it wound up as A. Okay, then tell me what is the additive identity? What is the number? It's a unique number. There's only one. And it's this number such that if I took any randomly selected number you would like, this one, and it's the additive identity, so my operation will be addition, and I want to add this identity, and it comes out identical. What is this number? 0. The additive identity is 0. It's the only number with that property. You add it to whatever you'd like, and it's unchanged, identical on each side. What about then the multiplicative identity? That's where I take some number. In this case, it can't be any random number you'd like. It's got to be a number different from 0. And I want to multiply it by some number called the multiplicative identity. And it comes out the same. What is that unique number? 1. 1 is the multiplicative identity. Actually, I spoke too soon with the a different from 0. You can actually have a be 0 here. Because 1 times 0 is 0. It comes out identical. Right? There's no such thing as a subtractive identity or a division identity. And that's because really there's no such thing as, well, subtraction and division are imposters. They're not unique. These are the two operations in algebra. There's addition and there's multiplication, and there's no other operations. That's it. Subtraction is built out of addition. Division is built out of multiplication. When we use, when we say something like a minus b, this is a convenient notation. It will never go away, despite what I said about it being fake. It will surely always be one of the operations on a calculator. But in reality, what is it saying? It's saying that you have this number a, and what are you adding? You're adding the number minus b. So, for example, 5 minus 3, many people will think about 5 minus 3 as here's 5 things, and then here's 3 things, the positive number 3. And then you have 5, and you take away 3 of them, and you have 2 left. And that's fine, it gets the job done, but the correct perspective is that you have the number 5 and you are adding negative 3. It's the correct, so this side over here is imagining like 5 doodads, and then you throw 3 of them in the garbage and see what you got left. And that act of throwing them in the garbage was like subtraction. But a more correct perspective is like what you have over here, where if I have my number line and let's have the convention that the number 5 is just an arrow that points to a particular point on the number line, and that place it points to has the name 5. And what is 5 really? It's really this green arrow. It's called a vector, and it points to the right because it's positive. So it's pointing towards the positive infinity. But the minus 3 is pointing towards the negative infinity. And how would you add 2 numbers? You would just put them head to tail. So then the red one is minus 3. And I took the tail of the minus 3 and put it right on the head of the 5. And then it would be pointing to a brand new spot on the number line whose name is 2. It would form a new arrow that points to the 2. So when you are looking at a minus symbol, surely do this. This is what everyone on the planet does, but sometimes you need to keep this in mind. Okay? And you could go even further, and we will right now. How did you get minus b to begin with? Well, you would have constructed it by multiplying a minus 1 times the number b. This idea will be essential. There's problems on this week's homework that 20% of you all will miss because we didn't observe that fact. That having this dangling minus symbol here, what does it mean? It means you have this object that's multiplied by minus 1. And we'll see those problems here shortly. Multiplication is the other operation in algebra. Let's not use an x for multiplication anymore. Use a dot, or use nothing at all. Juxtaposition, they would call it. The two symbols are next to each other. That means multiplication. And multiplication takes precedence over addition. When I'm staring at some expression, and they've got a bunch of stuff that's being added and multiplied and all this, I do the multiplication first, before the addition. And that's not math, that's just an agreement about how to read it, right? So that way there's less notation involved. And of course, if I talk about A divided by B, division is not a unique operation. It's always in terms of a multiplication, and all A divided by B means to us is A times the other number, 1 over B. So here was some division, and now I have it rephrased as multiplication, what it really is. So this number, 3/5, 60%, 0.6, is 3 times 1/5. It's 3 times 20%. That's 60%. Does someone have our attendance code? What is it?
402287.
Thank you. So see that this is correct. 3/5. Well, that's the same thing as 6/10. You can plainly see that that's 60%. And then 1/5, you know that that's 20%. So 3 times 20%, 60%. This observation is crucial. It's going to be hard to get everything done that we need to get done throughout the semester if we are stuck with the idea always that, if we're always stuck with this perspective and can never go back and forth. Okay, so we've discussed identities. Those are easy to remember. It leaves the thing that you're in. So we would say that these two are like rubbing together. You know, I take this and I rub this against it and it comes out the same, identical. And here, when these two have this operation, it comes out identical. And when I switch to that operation, it comes out identical. And that's why they say it's the identity. We've talked about how really there isn't subtraction. It's just a form of addition. And really, there's no division. It's just multiplication. It's multiplication by this number. And this is like a shorthand. It's a convenient writing. And everybody does it. Inverses. Yes?
Actually, I don't know how checking. You just write the code.
So to check in, you use your mobile attendance app. So another student will have to help because I don't know. How do we do it? No, it's okay. An inverse, every real number has an additive inverse. No matter what number you pick, there's going to be another number called the additive inverse, such that when I take your randomly selected number and add it to its additive inverse, I will get the additive identity. That's what the inverse does, is it takes us back to the identity. And likewise for multiplication, but that's where our caveat is, not every number has a multiplicative inverse. There's one number that no matter what I multiply it by, I'll never be able to get back to the multiplicative identity. So we'll start with an example. I randomly selected 3. And inside this box, I want to write down the inverse, the additive inverse of 3, which would cause me to come out equal to the additive identity. And what number goes in that box? Negative 3. Three together with negative 3 add up to 0. Can I generalize this and talk about the number a together with its inverse, and it comes out to 0, and you can tell me what the inverse is? Negative a. It doesn't take very much investigation at all to see what this pattern is going to be. Somebody picks a number, you stick a minus symbol on the front of it, and that's the additive inverse. It's got to be. This one, how far away from 0 is it? Well, it's a distance of a away from 0. And minus a is also a distance of a away from 0, and just points in the other direction. And when you put them head to tail, since they're the same length, but one goes one way and one goes the other, it comes right back to 0. You come right back where you started. Here's my randomly selected number. I want to multiply it by its inverse, and it has to come back equal to the multiplicative identity, which is 1. What number will that be?
1 over 3.
Say again?
1 over 3.
1 over 3. 1/3. Three times the number 1/3 is just 1. So this is like a third of a circle, and you got 3 of them. Well, that's a whole circle. Can I generalize this like we did a minute ago and say that a times something will just come out to 1? One over a. Pretty close. Is this always true? Can I say that this holds for any a under the sun? No. What's the a that's not going to work? 0. A has got to be different from 0. Zero has no inverse. You would be saying that 0 times some number is equal to 1, and that can never happen. That cannot happen. No matter what you choose, right here. Zero is a fairly new concept. It might be 1,000 or 1,200 years old, maybe just a smidge longer. the first person to ever goof around with it was, I can't remember his name, but he's a mathematician from India. And far, far away from all of the other scholars in Europe, he figured out that it was appropriate to use, and everybody else caught on. They wised up. So, and zero is, I mean, it seems commonplace these days, right? It's not something you want to see like for your bank balance, but I like it for my loan balance. And surely everyone in the room has heard this before. But can you explain it to me why? Okay. More rigorous though.
It doesn't, it just makes sense that it doesn't hold any weight. There's no value or amount in the number. So it's not going on your on your number line, for example, it's
Mhm.
not going to any direction. It's stagnant in the middle. So there's no, it has nothing.
So its arrow is just that point.
Mm-hmm.
It has no length. Okay. Look at an example that you know about. My favorite one is 6/3. What does this equal to? 2. But division is only in terms of multiplication. So the only reason we know this is equal to 2 is because 6 is equal to 3 times 2. That's how we know that this is 2, is because we have this. Okay. Well, suppose for a moment that you could divide by 0. Just suppose that this was a number. Now, I don't know what number it would be, so I'll just call it something. We'll call it n for number. And how would we have known that this was equal to that number? It would have had to be equal to n because 6 was equal to 0 times n. But there's a problem here, isn't there? What's the problem?
Because 0 times n would be 0.
Yeah. And then this would say that 6 is the same number as 0. So really, I could come back up here and put whatever symbol I wanted. And if I could divide by 0, like this says, then whatever symbol I chose to go in that numerator would be equal to 0. It would say that the only number you had in existence was the number 0. If you could divide by 0, you'd just have the one number, 0. And we know we have more numbers than that, so you can't. This is called a contradiction. I supposed that this was possible, and then arrived at a logical contradiction. Since the contradiction is there, it must be the case that this supposition was invalid, that you actually cannot divide by 0. another very popular just thing that people are told, and you're just kind of like the don't divide by zero. You just got told it once upon a time, and then they gave you a worksheet, and off you went, and you never really knew why, or weren't shown why it must be the case. This is really easy to show, surprisingly easy. I just make a couple of factual statements, and then at the bottom it shows that two negatives must be a positive. Does anybody know why this has to be? I mean, to me, it's just one of those things that everybody gets told and they just remember and don't ever really question. And you should question it. You should question, in math, you should question the validity of any statement that someone is making to you. You just assume that everyone's lying to you, and you need to verify it yourself. You need to see the logic, or else you're just memorizing stuff. Okay. Why is the multiplication of two negatives a positive? Well, it suffices for me to show that if a minus 1 times minus 1 is positive 1, that's good enough. Because I could have had minus a times minus b, and you know that minus a and minus b are each minus 1 times a and minus 1 times b. So really all I need to do is to show that the multiplication of minus 1 and minus 1 is positive 1. It's very easy to do. Start with the observation that 1 minus 1 is 0. I think everyone believes that. It's clearly true. And then I want to multiply on both sides by minus 1. So it would look like, here's my minus 1, and I'm multiplying on the left. And of course, because of the definition of equality, I need to also multiply by the minus 1 on the right. Okay, so I started with this that everyone agreed with, and I multiplied by minus 1 on both sides. Can we clean this part up? 0. So this is just still equal to 0. And now I need a famous property of the real numbers that surely everyone's heard of. I mean, unless you missed school from like 5th or 6th grade to graduation, you've heard of the distributive property. The distributive property is where you have it's just this statement. It's the assertion that this holds for every real numbers a, b, and c. This is the distributive property. And they call it this because it has the effect of having the a come in here and multiply times the b and the c. So I should take this minus 1 and multiply it right here and multiply it right here. Now I'm trying to show why multiplication of two negatives is positive, so I can't like use that information. I'll just be stuck having this minus 1 times that minus 1. I'll have to figure out what to do. The first multiplication with this minus 1 times this 1, here's what that would look like. We have our minus 1, and then it's times the 1. And then you have the minus 1 that we're distributing in times the other minus 1. And it's equal to 0. So the number that got distributed in is here. And then that 1 went there, and this minus 1 went right there. We okay? Can we clean up this part at all? So I want to clean this up. Which fact should I cite that we've covered already? Which definition?
The multiplicative identity.
Yes. I have a number. It's multiplied by the multiplicative identity. So this quantity must just also be minus 1. So now it says that minus 1 plus this product is equal to 0. You're essentially finished. Because if I wanted to know what this product right here equaled to, I'll just move this other term to the other side. And how could I do that? Well, this is minus 1. You'll add 1. And what property is that called that we're using? Additive identity. Here's a number. I'm going to add to it its additive identity so that I'm left here with, additive inverse. Here's a number, and we add to it its inverse so that what we're left with here is 0, the additive identity. So when I add 1 to both sides, it would now say minus 1 times minus 1 is 1, a positive number. So when I'm right here at this stage, when we added 1 to both sides, the minus 1 plus 1, those are each other's inverse. They'll add up to 0. 0 is the identity, so this terms plus the additive identity is identical to these terms because you're adding the additive identity. And now we're done. It's just a force of nature. It must be the case. When you multiply two negative numbers, it's got to come out positive. And this is why. Even if it's not very exciting. It's just a fact of life. All right, time for a break. Let's take 10 minutes. And when we come back, we will finish talking about discussion board.